Okay, so first requested topic is talking about converting between decimals and scientific notation. Big thing we need to remember about scientific notation. It's useful for ridiculously large or ridiculously small numbers, okay? And when you look at a number in scientific notation, you look at the exponent. If it has a positive exponent, then it's a big number. And I'm defining big numbers here as anything greater than 1. If it's a negative exponent, then it's a small number. And that's going to be anything that is less than 1. So if I've got something like 7, or I'm sorry, that's not 7, 47392.567, and I want to express that as scientific notation, I need to remember that scientific notation is always in the format of digit, point, digit, digit, times 10 to some exponent. And the times 10 is how many places I have to move the decimal to get it from where it currently is to where I want it to be. So I count jumps. It's going to be 1, 2, 3, 4 jumps. And since this is a number bigger than 1, this is a positive 4 exponent. The digits that go here, I've got 4.73, except because of this 9 here, I have to round this 3 up. So this becomes 4.74 times 10 to the 4th. Okay. If I have, let's say, a number like 0.000384001, I'm going to do the same thing. It has to be in the format digit, point, digit, digit, times 10 to some exponent. Now, since this number is less than 1, I know that my exponent is going to be negative. So I just need to see how many places I have to jump my decimal to get it between those first 2 non-zeros. So I'm going to jump it 1, 2, 3, 4 places. So it's going to be 10 to the negative 4. And I'm going to go with these digits right here. And I don't have to round because the 0 is not going to cause me to round, so it's going to be 3.84 times 10 to the negative 4. Okay. If you're going the other way, you're just inflating. I'm going like 1.79 times 10 to the 8th. Then the positive 8 right here tells me it's going to be greater than 1 when I'm done, so I know that I'm going to take this decimal and end up moving it to my right 8 places. So I start with 1, 7, 9, and I've already moved it from here. I've moved it 1, 2 places, 3, 4, 5, 6, 7, 8. So I jump at 1, 2, 3, 4, 5, 6, 7, 8 to get it right here. So that's going to be 179 million. Okay. Same thing if it's a negative. If it's like 2.24 times 10 to the minus 5. Then, since this is negative, I know that the decimal is going to be moving that way. So I start with my 224, and I'm going to put decimal, I'm going to put zeros out in front of it. I'm not sure exactly how many yet, but I know I'm starting with a decimal right here. So I'm going to jump it 5 places. 1, 2, 3, 4, 5. So it comes out to 0.0000224. Okay. On your calculator, if you're using a TI calculator, then you don't want to type in a number like 6.02 times 10 to the 23rd using times 10 and carets, you want to type in 6 decimal 02 second function, and then you want to find that button that's got the comma on it. It's got a little EE written over the top. That little button with the EE over it puts it into scientific notation, so it replaces that part, and then I just want to type in 2, 3 for my exponent. Okay, and that's true whether you use one of your big chunky graphing calculators or whether you use one of my little midget TI calculators. It's all the same. Any questions about that? Okay, and like I said on here, there's not going to be a lot of questions covering that stuff, but you know, it's not a bad thing to know how to do this, especially, you know, with numbers like that, because there will be a few times you might see numbers like that. Maybe not so much this semester, because we haven't really got there in stoichiometry yet, but definitely next semester it's going to be important. All right, so that's one down. Where to next? So what? Oh, I hate sig figs. Okay. Sig figs. Significant figures. Remember, significant figures are only important when you're talking about measured numbers. And it's a way to take some of the inaccuracy out of inaccurate measurements. The rules for sig figs, I think there's a total of 4 or 5 rules. First rule, if it's a non-zero, then it's significant. Okay, so anything like a 4, a 2, a 9, anything that's not a 0 is considered a significant figure. Okay, all the other rules have to do with zeros. Okay, if you've got a sandwiched 0, then it's significant. Okay, and that would be something like 2009. These two zeros are sandwiched in between non-zeros, so we count them both. They're both significant. Leading zeros, which are zeros that are out in front of all the non-zeros. So if I've got something like 0.0005, then leading zeros are not significant. They're just there as placeholders. Circle. Following zeros, which are the ones that are to the right of a measured number, or to the right of all the non-zeros, so like 20400, that would be these two homies right here. This is the only time when there's an if, okay? If there is a decimal, then they're significant. It doesn't matter where the number of the decimal is, but if there is a decimal that is being shown in that measurement, then they're considered significant. Okay? If there is no decimal, then they are not significant. Then, of course, numbers where you count something, like counting fingers, counting days, etc., those are infinitely significant because you're not measuring them. Only other thing having to do with this has to do with math, and there's 2 sets of rules for that when you're adding or subtracting. Now what you're looking for is you are looking for the least precise measured number, which is the one that goes out to the fewest number of decimal places. So for instance, if I'm adding 1.09 plus 22.6676 plus 15, what's my least precise number there? Again? The 15. It only comes out to the ones place here. So my answer, even after I add that all up in my calculator, is going to get rounded to that ones place. Okay? 6, 7, 9, 6, 15, 31, 7, so 5, 6, 7, 8. So 38.7576. I'm going to round that, so I would report that as 39. Okay. If you're multiplying or dividing, it's a little bit different. On this one, I'm going to count sig figs, and I'm going to go with the lowest number of them. So if I have, let's see, 193 times 17 times 6. What's the smallest number of sig figs in any of those three? Just one sig fig, right? This one here has 3, this one here has 2, this one here has 1. So I would start by calculating, that's a word, the numbers themselves, so like 193 times 17 times 6. I get an answer of 19,686. But since I can only use one significant figure, I would have to round it to where I only have one significant figure, which would mean that my answer is going to be 20,000 with no decimal. Is that too significant? Those following zeros are not. Okay. And again, very few questions on the test are actually going to be over this because I hate sig figs. Okay. Questions on those? Anything else? What's next? Does anyone besides Laney want to study something? Intensive and extensive properties. I love it. Okay. Okay. I'm not going to get very much into, at this point, physical versus chemical properties. But if you specifically want to know the difference between intensive and extensive, intensive properties will always be true no matter the amount you have. Extensive properties depend on amount. They change with quantity. So, some examples of intensive properties. Let me actually see if I can move this down here. Intensive properties would be things like color, melting point, boiling point, density, conductivity. Okay, how well something conducts electricity. How well something dissolves in something else, solubility. Whereas extensive properties would be things like shape, size, mass, volume, weight, height. Okay. So if I've got more of something or less of something, these things change. the way I think about it is, okay, let's say that I've got 1 gram of gold versus having a whole brick of gold, okay, which is like something like 150 pounds of gold. The things that are going to be true about both of those are intensive. They're built in, they don't change. Okay, so gold is always going to be shiny, it's always going to be gold colored, it's always going to be a soft metal, non-reactive, conducts electricity really well, no matter how much I have. Okay, it's going to sink when I put it in water. Whereas all these things here, like the shape, the size, the mass, the volume, the weight, the height, how much money I can get for it, those things all change with amount. So they're all extensive. Questions? Okay. Where's your next? Okay. All right. You want to go just talking about mixtures, or do you want to talk about all of the basic classifying matter? All right. That's fair. Okay. And I think you've got a flow chart for this that are in your notes somewhere. So all matter, which is anything that has both mass and volume, can be classified into 2 different groups. Okay, we can classify it as a pure substance, because it has a uniform composition. In other words, all the particles are the same. Or we can classify it as a mixture of pure substances, because it has a variable composition. It can change. Furthermore, we can split pure substances into 2 big groups. If you only have a single kind of atom, then you call that an element. If you've got 2 or more kinds of atom that are chemically combined, it's called a compound. Okay? 2 or plus kinds of atoms. And they are bonded together. So something like H2O is a compound. Something like O2 is an element. You see 1 kind of atom, here we've got 2 kinds of atom, but they're always joined together in these little water molecules, and so the particles, even though the particle here is a molecule, the particles are always going to be the same. And my mixtures, they're divided up into 2 big groups also. They're divided up into homogeneous mixtures. Okay? Homogeneous mixtures exist in a single phase. Either they're all solid, all liquid, or all gas. They appear to be a single substance. Okay? Another name for those, we call them solutions. Solutions can be gases, liquids, or solids. Okay? So we can have something like salt water. We can have something like air, or we can have something like steel. You can also have heterogeneous solutions. Almost ran out of space there. Heterogeneous solutions exist in multiple phases. You can see that they've got chunks. Okay? If they have chunks, If the chunks are very, very tiny chunks, then we say that these are colloids. If the chunks are not so tiny, but they're big enough to actually see and they're big enough to actually settle out, if you stir them up and then leave them alone for a while, then we call these suspensions. One more thing I'll add, sometimes it's hard to tell the difference between a compound. I'm sorry, no, that's a lie. Back up. It's hard to tell the difference sometimes. Keep backing up. Come on. I do. All right. Between a solution and a colloid, because a colloid can look like a solution at first glance. The test that you can do with that is to shine a bright light through it, okay, like a laser beam. These guys here scatter light. These guys over here do not. And that's just about all the time we have today. So for tomorrow, please finish looking through this list. Circle or highlight things that you want me to go back over. We'll test on Wednesday. I will see you tomorrow.